Hey guys, in this video I'm going to be explaining how a SquID to point algorithm works, and we're going to be coding it, and of course we're going to be coding the commands to make it work. If you're not using command base, you can watch the algorithm, or I would highly recommend looking at my last 3 videos and at least consider using command based architecture if you're struggling to find an architecture that works for you. Anyway, with that being said, let's jump right into how a SquID to point works. So first of all, let's do a quick introduction to closed loop control because a lot of people aren't familiar with that, and I just want to do that. So basically, a feedback controller is a controller that takes in the error of a system and generates an output power based on various coefficients. And the most common controller used, the most common controller used is a PID controller, or a PID. I know people will be annoyed if I say PID, but a PID controller, while very effective, can take a long time to tune and assumes zero friction in the system. And usually this is corrected through gain scheduling, which is basically changing coefficients based on the situation, or feed forward, applying power to compensate for anticipated behavior. And this is a really solid solution. It works really well. The thing about this is that they take a long time to tune, and they don't really solve the fundamental issue that your PID controller doesn't accurately model your robot's behavior. And so one of the solutions to this, it's not the end-all be-all solution, and it's probably isn't the fastest either, because you can argue that the derivative term of a PID controller will break it faster, but a SquID controller is much easier to implement and tune and more accurately models your robot's behavior. So if you're looking for, I'm not going to go over how SquIDs work and why they work, but if you want to look at that, you can look at Escape Velocity's video on the subject, which is SquID controller explanation video, that's what it's called. Highly recommend that. But anyway, if you're completely new to feedback control and you just want a good idea of how like feed forward works, how PID controllers work, I would highly also recommend looking at KookieBot's video. They have a video on PIDF loops and how to tune them. I would definitely look at their video on YouTube as well. So now let's go to this. How do we use this feedback controller to move to a point? So we just talked about how it takes in an error and then generates an output power. So in order to generate our output powers and our error, the robot checks its position error and its heading error, and then we divide everything into 3 components. So we have our translational components, which is X and Y, so 2 components, and then a heading component, which is how much you need to turn. And so then the tricky part about all this is that you might think, you could just put deltas on everything and associated controller to everything. We need to rotate the vector first because, and I'll show you why if you are not familiar with this. So basically, if this is your robot and this is your target, assuming this is at 0 degrees and assuming a static heading, you are going to have these nice deltas right here. These are your error vector, and if you have a controller associated with each one and just plug it into your strafe and drive mechanic kinematics, then it'll drive nice to the target in a nice straight line very efficiently. This is very nice. But the problem is, as soon as you add in a heading error like this, then what your deltas are going to be from the robot's perspective, and the robot's not going to know how to deal with that. So what's going to happen in something like this is it's going to basically, assuming this is at 0 degrees, that's a big assumption, your heading is going to take a while to catch up, and eventually it will, but you don't want this curve unless you're going for that. But don't do it this way, please don't. So what we want to do is we want to rotate our error vector so the robot's perspective is still adjusted, but it still has a heading error which it can correct for. So each moment in time, as it's driving to its target, it's constantly looking at its error and rotating it to a field perspective, and then calculating its power to drive to the target while turning in the most efficient way. Alright, so that's pretty simple. I think that explains it pretty well. And then, yeah, of course, after that, after you rotate the error, you just use your feedback controllers for each component, and it's basically that simple. So now let's go ahead and get to coding this bad boy. So the first thing I like to do when coding this is making a point class. There is the pose2D class that's built into the SDK, but I don't like it just because I don't like typing inch every time. It's kind of annoying to me. So instead, I'm going to make my own point class, which you can, I will timestamp this if you want to skip past this. That's perfectly acceptable. You don't really need this. You can just use the pose2D class. And for some reason, this is being really silly. I do not know why, but for some reason I can't access my new menu, so I'm just going to do this. Okay, we're just going to add that, and we're just going to delete all that. Well, yeah, we're going to delete all that. So just public class point. And then, of course, it needs a package name, so there. And we don't need to extend anything. This will be a very simple class. Now, one thing that I haven't shown yet is in here, in your module of team code, you need to copy this in. This will just make your life easier. Again, this is an optional step. This will be in the description of the video, but these are just getters and setters. And so they basically make getters and setters an automatic process. So you just have to do add getter and add setter. So here, I'll show you what I mean by that. Oh, stink. Alright, so the first thing we're going to do here is we're just going to make a few private variables. So private double x, y, and I'm going to put a space there, y heading. And we're just going to, above this, we're just going to say at getter and at setter. And that just makes the life easier because you don't have to make a function for setting each one of these. It stinks. So then we're just going to make our constructor. So public point, and we're going to take in double x, double y, and double heading. And then we're just going to say this dot x equals x, and so on and so forth. And I like to make a default constructor. This is definitely optional, but it does make your life a bit easier since you don't have to actually make a constructor every time. So just say public point and just don't take in anything, and just say this dot x equals 0, this dot y equals 0, this dot heading equals 0. And then below this, we're just going to want to say public void set point. And all we're going to do is just say this dot x equals, well, actually, all we have to do here is just copy in this. It makes our life easier. Boom. And so that's your set point function, and that's the whole point class. It's not that complicated. So then let's also go ahead and make our SquID controller, which is also not that complicated. So SquID controller add. So all we need to do is say private double ksq, and then below that we're going to make our constructor. So public SquID controller, and then double ksq, and just say this dot ksq equals ksq. Below that, we're going to want to make our calculate function, which is going to be public double, so we're going to want to return a power calculate, and we're going to take in a double error. And above this, I'm just going to put so in here, I'm just going to say that error is generally target minus measured value, and then I return the output power. I cannot type, oh goodness. Okay, so in here it's going to be pretty simple. We're just going to return math.square-root times math.absolute value of error times ksq. I'm pretty sure you can put ksq outside this, but it doesn't really matter. It works either way. And we're going to say times math.signum of the error, which basically just returns -1 or 1 depending on the sign of the error. And there, that's all you need to do. It's pretty simple. So then going back to our drive class, we're going to want to make a few things. So first we're going to want to make our target point. So private point target point, and let's just go and say new point there. And then we're also going to want to make our two SquID controllers, one for translational and one for heading. You can definitely use 3 SquID controllers, so one for your X, one for your Y, and one for your heading. I prefer to do it this way, but it just makes your life a bit simpler because you don't have to tune each one. So we're going to make private SquID controller, heading controller, and I'm just going to say equals new SquID controller. And in here we're going to put our constant values. So for now, just put 0.0, and the same for the translational controller. Oopsies. SquID controller translational controller equals new SquID controller 0.0, and there. Oh, this reminds me, go ahead and go back to your SquID controller, and this will make tuning easier. This is definitely not a required part of the process, but you probably will want to do this. Just say public void set KSQ and just say double KSQ this dot KSQ equals KSQ. There. So let's go back to drive, and we're also going to want to make our error vector. So private vector2d error vector equals new vector2d. And I believe this is all the components that the last thing we need is private double heading error radians. And there. That should be all the components we need for our function. So down here, we're just going to put above stick input public void driveToTarget. And in here, we're going to first calculate our error. And the way we're going to do that is just going to say heading error degrees, let's start with that, equals AngleUnit. This is important to normalize this because otherwise, basically your robot will take inefficient turns to get to the desired heading. So for example, if you're at 359 degrees and you want to get to 1 degree, the delta of that is a huge number. And so your robot's going to turn counterclockwise instead of clockwise to get to that target, and that's no good. So in order to do that, in order to calculate our heading error, all we have to do is we have to say our target, which is going to be our targetPoint.getHeading, and then yeah. So I'm actually going to convert this to radians right here. That means we don't have to do it right later anywhere. It makes our life a bit easier. And then we're just going to say minus robot heading radians. Then below here, we're going to say our error vector equals new vector2d, and our new vector2d is going to just have the robot, our targetPoint.getX minus our minus our robot x inches, and then it's going to have targetPoint.getY minus our robot y inches. And of course I did funny parenthesis thing. Yay. Okay, there. Why are you sad? Oh, you don't need that. There we are. So next we're going to rotate our vector, which is pretty simple. All you have to do is do error vector equals error vector dot rotate by, and we're just going to say minus math.toDegrees robot heading radians, and there we are. And so then after that we want to calculate our powers. And so our turn is going to be minus heading controller dot calculate heading error radians, and then I guess I have that in there from earlier. Okay, so then after that our strafe, or our drive, is going to be error vector dot getX, and then our, well, that's not going to be too good, equals translational controller dot calculate heading error vector dot getX. That should be better, and not dot .getY dot getX. There. Okay, now we have strafe, and that's just going to be equal to, again, minus translational controller dot calculate error vector dot get y. And so there, that should work. Let me make sure this lines up, because last time I did this, things did not line up, and it looks like we're good. So yeah, that all should work now. So this is the fundamental algorithm. If you're here for this, this should work once you tune your numbers and all that stuff. But definitely stick around, because we're going to be making the actual tuning OpModes, and this doesn't really require a command-based architecture. It just makes your life easier, so definitely stick around for that. And we're also going to be making some functions to confirm whether we're actually at our target or not. So both of those are very crucial if you want to implement this into your actual code. So anyway, now that we've made driveToTarget, we're going to start working on our tuning OpModes and our supporting structure. The first thing I'm going to actually do is just make a function called tuneHeading, and we're just going to put this right above our read function. So public void tuneHeading, and we're just going to take in double KSQ, and we're going to say heading controller dot set KSQ KSQ, and we're going to say telemetry dot add data, and we're going to say position, which is our robot heading degrees, or rather radians, and then telemetry dot add data, target, and we're going to say targetPoint.getHeading, and we are going to want to make this Math.toRadians. Yeah. Alright, so that should be our tuneHeading function, and now we're going to make a function to tune our translational. So public void tune translational. So again, we're going to take in double KSQ, and we're just going to say telemetry dot add data, position, which is going to be our error vector dot magnitude. And so this basically just gets a general view of your translational components. You can definitely do this differently and like separate it out into the individual components, but this just makes your life a bit easier. And then again, we're going to add telemetry.add data, and we're going to put in target, and our target is just going to be 0.0, so that just gets us our reference line. And I am forgetting to do translational controller dot set KSQ KSQ. And there. Now we can make our OpModes, so let's go ahead and do that. I will say, I'll just go ahead and say this now. It will save you so much time just to make a wheel direction debugger. Like basically all you need to do here is import your localizer, import your motors, and inside your loop function just say, like if gamepad1.a set power 0.2 0. And so on and so forth, and then put telemetry to output the name of the motor you're actually wanting to use. And that means that you're double checking your wiring, you're double checking your reversal, make sure your reverses are correct, and you're also double checking all this other stuff. So also your odometry pod directions, those are also very important. Make sure to make this OpMode. It'll just make your life a whole lot easier. Also, I am just gonna real quick, just in case people are copying this, do this for each motor, because otherwise when you set it to 0.2, it'll be 0.2 indefinitely, which is no fun. So right front dot set power 0.0. I already have this done, so I'm not even gonna do this right now, but anyway, we're gonna make our other tuning OpModes now. So heading tuner, add, and we're going to extend command OpMode, just so everything's updating. It makes your life a bit easier, and it's going to ask us to implement our methods, so we're going to do that. And we're not going to import our robot into this, we're just going to do our drivetrain, so that makes our life a bit easier. And I'm going to copy my constructor from my reference. So that is going to be here and here. Because this is going to be different for everyone depending on your hardware and all that stuff. So before we do that, the first thing to do is to say telemetry equals new multiple telemetry, and then put in the FTC dashboard telemetry. .get instance, .get telemetry, there. So that means it'll output both on the phone and the FTC dashboard. Then down here, we're going to say command scheduler .get instance .schedule, and we're going to say new run command drive read new run command drive loop new run command drive write. And also we can do a new, no, we're not going to do that actually, my bad. So in our, we're also, instead of just doing the initialize function, since this is a tuning not mode, we're going to need to override the run function. So we're going to override public void run, and we're going to go ahead so we don't forget, say super.run. That'll run the command scheduler, so we don't want to forget that. And in here, we're going to just say, first of all, stick input. So drive.stick input, and just put 0, 0, 0 for all of those, because this is just to make sure the motors don't get set to a power and then run indefinitely. That would be bad. And so then below that, we're going to say if gamepad1.a. We're going to say drive.set. Oh, this is, forgot to do something else again. So back here in drive, we're just going to say public void set location, and we're going to say just take in a point, and we're going to say pinpoint dot set position point, and this is going to ask for new post 2D, so point, or rather inch first, then point dot get x, point dot get y, and we're going to put radians, and then finally point.getHeading. Of course, this is going to have to be converted to radians, so don't forget to do that. About half the bugs I make are due to radian degree conversions. So that will set our location. We're also going to want to make another one that's public void recalibrate IMU. So just pinpoint.recalibrate IMU. And then finally, we're going to want to make one that says public void set target. And we're going to take in a point again. And we're just going to say target point equals point. It's giving us a warning. Yeah, that works. You could definitely do this. I'm going to just leave it this way. But yeah, you could use a at setter for this for sure. So let's go back to our heading tuner op mode. We're just going to say drive.set location and just say new point, and that'll be our default constructor that we made, so 0, 0, 0. And then finally, we're going to say drive.recalibrate IMU. So now these are not going to be silly. So if gamepad1.a, we're just going to say drive.set target point. New point, so that's going to be our return position, and then our driveToTarget, and then we're going to say else if, and of course I forgot the if there, gamepad1.b, we're going to say drive.set target point new point 0, 0, 180. Then below that, we're going to say drive.driveToTarget. Then after that, I believe we should be done except for our telemetry. So we are going to have to add in up here a public static void SQH, so our square root term for our heading. And this is going to be double, obviously, I just forgot. Not void, oh my goodness, okay. Then we're going to say drive.TuneHeading, and we're going to input that so SQH, and then we're going to say telemetry.update. So yeah, that should work. Aside from that, we just need to make this the exact same thing basically, but for translational tuner. And I am forgetting to add @teleop and @config. So don't forget to add those things. This is what allows you to actually edit this number in your FTC dashboard. So we're going to do those two things. So just copy, well, actually just copy the whole class and then paste the whole class and then translational tuner. And the only difference here that basically is we're going to set this to SQT for translational, and that's good, but we need to say tune translational, not tune heading. And then here I like to change this to 90 so that way I can see both components working at once. And then you can obviously leave the heading off. It's really completely optional, but it does kind of give you an idea of how it works as a whole and not just one component. So then our X is going to be 24, which is about the size of a tile, and Y is going to be 24. So that should be done there. And so we're basically done at this point. We're ready to tune. If you're here for tuning and everything, you could do that. And now we're going to make the supporting structure to go with this. So we're going to say public, no, not that. Public boolean is in radius. And we're going to say new point, or rather a point, and double radius inches. And so in order to do this, we're going to make it pretty efficient. So the way to make it the most efficient way, I'm going to have to look at my reference for this, but basically you're just rearranging the Pythagorean theorem to compare two variables. So first we're going to get our x delta. So our double x delta is going to be our robot x inches, but of course we need to do point.getX minus robot x inches. Then our double y delta is going to be our point.getY minus robot y inches. Then our we're going to want to get our squared distance. So double distance squared is going to be x delta times x delta plus y delta, not equals, plus y delta times y delta. And there's that. So then after that, all you need to do is say, is our distance squared less than equal to our radius squared? So return distance squared less than equal to radius inches times radius inches. So yeah, that should do it. Now we're going to use this to basically make our is@target function. So again, public boolean is at target. And first we're just going to have to make a few timers. So let's go up here and say private elapsed time target confirmation timer. And we're just going to say equals new elapsed time. Makes your life easier. And let's just copy that and say over time protection timer. So basically what we're going to do is, if we're in our radius, we're going to say basically do a countdown, and once we're in a radius for a certain amount of time, we're going to say we're at our target. But if we're driving to a point for 4 seconds, we know there's probably something in our way, and so the response I'm going to code in here is just to give up, because that's the simplest and most effective way to do it probably. You can also do crash detection, but that's a bit complex. So what we're going to do is we're going to say if we are not in radius, and we're just going to say target point, and our radius can be whatever. I like to make this an adjustable constant at the top, so that way you can adjust it tier-like theme, so private final double radius threshold inches. It's not liking me because I haven't defined it yet, but it's also, and this just needs to be like 0.1, not a big number at all. But I obviously misspelled something throughout there. Okay. And we're also going to make a heading threshold. And this is going to be in degrees. I like to make this pretty generous, like upwards of 20 degrees, maybe even 25. It doesn't need to be that small, and it'll basically travel 20 degrees in 100 milliseconds, so not much to worry about there. So we're going to say isn't radius, and then radius threshold inches. So if we're not in our radius, or rather, it's definitely an or we are not in our heading. So robot, how do you do this? Math. Okay, yeah, so math.absolute value of our heading error, radians, is greater than or equal to, and this needs to be 2 degrees, our heading threshold inch degrees. So if both of those conditions are true, then we do targetTimer.reset. And then after that, we say, basically just say if target confirmation timer dot seconds is greater than or equal to, okay, we need to make this number. So private final double target confirm seconds. And then of course I swapped these two around in my head. This is actually going to need to be something like 3, so around a 6-inch diameter circle. That's might seem generous, but you'll still have like less than ½ inch accuracy. That's just if your localization gets off and you hit something, it's not going to matter. So our target confirmation seconds is actually going to be 0.1, not our radius threshold inches. Goodness, I cannot think today, but that's fine. So we're just going to say target confirmation seconds, goodness, okay, is greater than or equal to target confirm seconds. So each time through the loop, we're going to check if we're not there, and if we're not there, we reset this, else it counts up until it's greater than that. So this actually needs to be returned. And then after that, we're going to say or overtime protection timer dot seconds. You can adjust that. I'm not going to make this a constant. Greater than equal to like 3.0 or something. So yeah, there we are. There's our target function. Obviously, the problem with this is that it's going to basically drive to its target, and once it's there, then these timers are still greater than, and so this will always return true. So what we need to do now is make a trajectory start sequence. So public void trajectory start sequence, and we're just going to say target confirmation timer dot reset and overtime protection timer dot reset, and there, that should be everything. Now we're going to make our commands, but before we do that, we're going to actually tune everything, and then we're going to make our commands, and then we're going to actually write an autonomous route that just goes in a square so you can see how it works. Alright, so now we're to the tuning part of the process, and so what you're going to want to do is go and connect to your robot's Wi-Fi and then log into this URL in your web browser. This will be in the description for your convenience. And you're going to want to basically go to this heading tuner. Well, start the out mode first of all. Start that, and just start out with like a small number like 0.01, which probably won't do anything, but we're going to try it anyway. So as you can see, we get our live telemetry of our position, which is hardly changing at all. This is just a tiny bit of IMU noise. So yeah, we can press the button, and you can see that the robot is actually moving, when we press the button, but that doesn't mean it's moving as fast as we want it to, so we're gonna bump it up to 0.05 maybe, see if that makes a difference. Okay, so it is moving a whole lot faster now. Now it's kind of actually trying to reach its target, but obviously this isn't good enough, so let's go to 0.01 and see if that works. We're almost getting to our target, but as you can see from our graph, our lines are not quite yet meeting yet. So let's go up to 0.03 and see if that works. That's looking a whole lot better. And also, if you're wondering why these two are off, don't worry about it. It's just the angle wrap bug with the telemetry. So yeah, you can see we're very, very close. We could still do better though. So let's go to like 0.04, see what that does. And that's looking a whole lot better already. And we're not seeing oscillations yet, so that means we can go faster. So let's go up to 0.05 and see what that does. That is looking pretty sweet to me. We can probably go up to 0.06, see what that does. We are seeing a little bump now, which isn't necessarily a bad thing. I think I'm going to leave it at 0.55. That seems like a pretty solid constant to me. We're getting a very fast response from the robot, as you can see from the screen, and this is just beautiful. So let's go ahead and copy this constant and go back to Android Studio and paste it in before we forget. And yeah. So we're just going to want to put this right here in our heading controller slot. And now we just have to run the translational controller, although we do need to go ahead and program the robot, because otherwise our heading tuner won't be saved yet in the op mode, which is definitely something you could change in the configuration so you don't have to program the robot between this step and this step. But yeah, I'll see you after I program the robot. Alright, so we are back, and now it's time to run the translational tuner. So basically just follow the exact same process as before. Initialize your op mode, start it, and log the position and target. And what we're going to do is just slowly increase this number from like 0.01 until we start seeing the robot do what we want it to. So I do expect that it will start to move. So as you can see, yep, it is. But we aren't quite getting to our target, so we can definitely stand to increase this just a bit more. Let's try 0.02 and see how that does it. That is looking really good, but we're still not quite to our target yet. We're still, 0.03 inches off. Not good enough, obviously. So let's go to 0.025 until we start seeing some actual oscillations. Obviously, it's very important to look at the robot and not just your graph, because that's sad. And as you can see, our robot is overshooting a bit. I think a good constant here would be 0.025 or 0.0225. That seems like a pretty good balance between these two. So yeah, as you can see, the robot's doing exactly what we want it to. It's going back and forth and turning while it's moving, and everything is beautiful. So let's go on ahead. Do not forget to copy this constant and put it back in here on your translational controller. Alright, so now that that's done, we are going to move on to making the commands in our drive command class. Let me transition this back to this. Alright, so to make these commands, it's going to be pretty simple. So let's go to our drive command class and go to public static class driveToPoint. And this is going to extend command base. And we're going to want to add in our drive. So private drive, and we're going to obviously want a point. So private final point. And this is also going to be final, but it doesn't really matter. Then we can hover over that and do Alt-Shift-Enter to put it in our constructor, and we're going to add the requirement of the drivetrain. That's important for the command-based architecture because it means it won't try to run another command that requires this subsystem. So then down here we're going to say @override public void initialize, and this is just going to say drive.trajectory start sequence drive.set target point, and just input the point. And then we need to basically tell the scheduler when we're finished or not. So at override public boolean is finished. That's going to be the method we're overriding. So we're just going to say return drive.isATarget. And there, that's your driveToPoint function all done for your command. And then down here we're going to make a turn to heading because I'm assuming y'all are probably going to want to use that. So public static class turn to heading extends command base. So let's just go ahead and copy everything in here. This will make our lives just a bit easier. So change that to turn to heading, and then for our drive, instead of a point, we're just going to do double heading, and just copy that, copy that, copy that, copy that. Okay, and then that needs to be a double. So that's our constructor all adjusted, and then set target point. Let's go ahead and make a set target heading method. That's something I should have done earlier. So public void set target heading, double heading degrees. And so just targetPoint.getHeading heading degrees. And there we are. So then we go back to our drive command and we just say set target heading and heading. And there, that's all it is. Now we're going to actually make an autonomous OpMode that uses all these functions. So up in our OpModes where we've made our teleop, we're going to make a new package, and mine is a bit weird for some reason. It has like this OpModes.teleop weirdness going on, so if yours is doing the same thing, just do OpModes.auto and that'll fix that. And then just do Java class. Let's just call this go in square. We're going to add that, and then this is going to extend our command OpMode. And first we're going to instantiate our robot, so private robot, and it's going to ask us to import the class because I can't make it capital because that interferes with the other class, which is unfortunate. But anyway, private robot, and then we're going to make, yeah, that should be good. So now all we got to do is add in our initialize function. So do that, and our initialize is basically just going to say, and so our initialize is just going to define our robot. So robot equals new robot, and it's going to want our telemetry, our hardware map, and I'm going to go ahead and just say auto and import that as a static constant. That makes it a bit cleaner. And then we're going to say robot.drive.set target locate or set location 0, 0, 0, not that, new point and 0, 0, 0. Oh, we don't actually need that because of the default constructor. And then we're just going to say robot. Oh goodness, I keep doing this. Robot.drive.recalibrate IMU. And then after that, we can actually schedule our commands. So robot, not that again. Okay, so control shift or shift home, delete. Okay, robot dot schedule, and here we're just going to say new run command. New run command, robot read, new run command, robot loop, new run command, robot write, and then another new run command, robot.drive, and this is just going to say driveToTarget. Yeah, just like that. Then after that, we're going to put in a new sequential command group, so everything runs in a sequence and not all at once. I've made that mistake before. Back in my early days, didn't really work well. So all this is going to say is we're going to have a new driveToPoint command, and we're just going to say 0, well actually yes. So we need to put in our drive, so robot.drive. And then below that, we're going to just say new point, 24, 0, and also 0. Then we're going to have a new turn to heading command, which is going to be a new, or rather robot.drive, then new point, 24, 0. Oh no, that's not right. So all we need to do here is just say minus 90, I believe. Right? Because no, it should be 90 because we're turning clockwise, and think of the unit circle, that should be correct. So then we're going to want another new driveToPoint command, robot.drive, and we're going to say new point, 24, 24, 90, then a new turn to heading command, robot.drive. This is going to be 180. Then new driveToPoint command, robot.drive, new point. You know what? I'm just going to skip this process. I think everyone's bored at this point watching me code this. But basically, we're just making it run in a circle. You can play with this as much as you want. It doesn't really matter how you do this, but you can just input your driveToPoint commands, your turn to heading commands to follow whatever path you want to at the end. And at the end, I'm just going to make sure this works and run it, and we'll end the video just with that and me doing a nice outro monologue, which will be, I'm sure you'll be very interested to listen to. So this here is the final code if you wanted to copy it, and up here we're just going to say @autonomous. Alright, so this is the finished product. It goes in a square very nicely. And in the next video, I'm going to be adding waypoint functionality to this algorithm, which basically means you can follow waypoints and not lose much velocity between the waypoints. Of course, with this current iteration, you have to stop at each point, which isn't exactly ideal. So in the next video, that's what I'm going to be working on and sharing with you. We had a very similar system this year, and it was very fast, very efficient, and I honestly think that if you're in a time crunch and you're as lazy as I am, because that's what this series is all about, that it's basically just as good as Pedro pathing. Like, obviously Pedro is going to be better. You have splines. The splines are just subjectively more efficient in a lot of ways. However, if you're just trying to get something that works and trying to throw something together, and the week after your hardware team has thrown something after you, this is really the perfect solution for you. So definitely look at that video and consider looking at the last videos where I discussed the command-based architecture. And with that being said, enjoy your point-to-point algorithm, and I can't wait to see what you guys do with this. So have fun.